Okay, so I was thinking about so the idea here is basically tell you a little bit of the history, how we develop the code and what does the code do. So the problem was, again, if I go back to this one, okay, so this one is the main issue. Now, there are a couple of reasons why I was interested in following this kind of growth in this way. So going from something that looks like this, a pyrene, the need was to go this way, so to follow this way for few reasons. The first one is that in the moment you have so much chemistry, you can understand more about the pathways. So for example, think about a sphere, but then compare with something that is like a three-dimensional, very convoluted. In the moment you have structures, you can tell me something also about the type of reaction that can happen. So if you have something that is, all maybe folded or weird, and you are thinking that maybe a naphthalene can come in and react, then having structures like this can point you also some limitations. So for example, how likely is that, I don't know, a naphthalene will get in an inner side of these structures? So having the structures give you information about the type of steps that can follow that. So that was one of the reasons to do that. And the other one is that I was very much interested in the health effect of nanoparticles. So in order to assess those, you need to have some information about the structures. So when you talk about the health effect, and you talk about the big system here, like the Soot, if you think about the Soot can be stopped, right, even with a car or a filter. But what really comes out is more those nanoparticles, that there is no way right now to stop them. And so the question I had was, what are the health effects of those carbonaceous material that you form from combustion and have this kind of size, basically? So I wanted the structures. With this kind of desire comes the problem because of the time scale. So MD brings me to up to certain size and time. Continuum is now what I wanted. And so we decided to do initially a combination. There was a kinetic Monte Carlo and a molecular dynamics. And this is what they call AMPI code. That was a few years ago. Now we call it a little bit different, but the idea is this kind of loop in which, as I was mentioning, so Monte Carlo does not have, if you want a velocity, you are just jumping in space, like from here to get to these new structures, right? And so given the idea was you have your molecule, a gas phase species that is now needs to grow. You know that is in some kind of environment, so you know that the gas phase maybe has acetylene, has hydrogen, has other species. You do need information about the rates that you can have there. And so what happened is that the kinetic Monte Carlo will take a step. We'll say, okay, my favorite reaction, the probability that this reaction maybe with C is the highest one. And so you will jump from this guy to this one. Now what happened is that maybe C is added here, but it's not necessarily the minimum, the more equilibrated configuration. But the one that is really equilibrated is this one. I'm just giving you an example here, okay? So KMC allow me to jump from this configuration to this configuration. MD in this initial version was taking me to, if you want, a local minimum. So from here, you minimize the structure, and now the final one is this guy here. Okay, so I was combining both of them, and the idea was to have different time scale. KMC that was jumping for like longer time scale, and MD to equilibrate the molecule, it takes into account the rearrangement that you can have here. So that was the initial story. So there was AMPI. We had a lot of, we had success with AMPI, but computationally was always a little bit, was time consuming to do simulation. And so eventually we have modified this code. The idea is still the same, but we got rid of the molecular dynamic part, and we are right now doing everything with the kinetic Monte Carlo, but we impose additional criteria to kind of take into account this. But again, the idea is the same. You have a seed, an initial seed, and you have some reactions that can happen, the list of reactions. Monte Carlo allow you to grow. There is a difference though, so here is a little bit, someone asked me the reaction also. So right now we call it SNAPS, so we changed a little bit, but it's the same idea. So it's stochastic nanoparticle simulator. And again, you have a species, and you know that the species is placed in some kind of gas phase environment. So you can have an OH, you can have, this is a C3H3, a propargyl. If you remember, for the first day I was telling this is a key species to grow structures. Then there is an acetylene, there is a hydrogen, different species, and you need to know some temperature. And so what happened is that given a list of possibility of reaction, K&T Monte Carlo will advance the system. So it will say, my benzene is going to react, I don't know, with an OH here, and then you have a new situation. So the first thing I want you to see is that you remember the big R, that is the sum of all the rates that you have, basically. So every time your delta T, when you jump, is the ratio between a random number that you can generate divided by the sum of all the possible reactions that can happen at that time, okay? And so if you have reaction that have a different speed, again, if you have a slow or high or very long time reactions, then your delta T is taking into account that. The problem is that sometimes, you know, one of the tricky that is that there are a lot of reactions that can happen. So if you have a high temperature, for example, chemistry really likes high temperature. So if you have a 2000 Kelvin, this number is really big because a lot of things can happen, right? And so your delta T is very tiny. So you don't move much. If you're at a low temperature, only few reactions happen usually because the chemistry is not what is driving. So this delta T is a small, this denominator is a small, your delta T is going to be big. Okay, and that's what that actually is also the beauty, because on the other side is flexible. So depending on the system and the type of reaction you want, the event that you want to follow, your delta T adjusts to this. Okay. And that allows you to go also to milliseconds if you're interested, so moving in time. And so what SNAPS does is basically simulate a trajectory, okay, described with the time history of the chemical reaction. Now, the difference here is that differently from what I showed you before when I was talking about Frank Clock, when I was talking about Kraft, they had a list of reactions in which they had the pHs, and then you maybe are adding acetylene, and then you have other structures moving. The way we define SNAPS instead is with the reaction sites. So we are no longer saying, you know, this is like a benzene plus, this is your aromatic here. Okay, I give a name to this, but I don't care anymore. I consider that as a site. So if I have an acetylene, the acetylene is added to, for example, a carbon and an aromatic ring. It doesn't matter if it's a benzene. It doesn't matter what's after that. This is an addition, for example, of acetylene that can happen to this radical, but the sites are defined as a radical site, a carbon with the radical sites. Okay? And so what these allow me is basically, I don't need to know what happened next. So it's not that I'm going like, you know, I need to know this guy. I'm here in the moment. And I'm just saying A can be added to the radical site here. The system will evolve and bring me to this kind of species here. Okay? So I don't need an a priori knowledge of my product. And this is one of the beauty of this approach, because you remember, one of the reasons why we don't match, that I was showing you yesterday, is discrepancy between experiments and modeling, is that maybe the rates are not perfect, but maybe we don't have the whole pictures. It's because we bias the system. We need to know what's happening. With this approach, you don't need to know that. The system will evolve you, will add the C, for example, in this case, and will build these new structures. Okay? I don't need to know that in advance. And so you can see structures like these that are built. And again, as a gas phase species, I have the gas phase, I have the temperature, and I need a list of the reaction rules and rates. Okay? So one of the tricky parts is also to translate the reaction that is, I know, benzene plus acetylene in something that could be read by the code. And so this is an example of a trajectory. So what happened is that, again, there is no a priori knowledge. I know that I can add, so here, I have, this is a naphthyl, is a naphthalene with the removed nitrogen. So I do know that there is an active site here that I could You could add acetylene. So the next jump is this. So the next jump for me is addition of acetylene to a radical site. It's not addition of acetylene to a naphthalene. Okay, and then this is eventually just a trajectory of what kind of pHs you form. So, and again, what I mentioned is that this helps you to identify some pathways that maybe you were not thinking before. So just to give you, this is a movie, this is something that we produced in a flame to see how this works. So if you think about really the flame, that is everything that we're talking about is about the flame, and you know very well when you have the yellow material, when you have a yellow flame, you're forming these materials, basically, the nanoparticles. So this movie is just showing you this Monte Carlo trajectory. So you start from a pH, and what you're seeing here are the jumps that kinetic Monte Carlo does. So kinetic Monte Carlo is either adding something slowly to the system, or is maybe removing something. And so the beauty is that, first of all, green is carbon, white is hydrogen, but you can see how things are evolving over time, basically. You can see what are the product, what are the species that you get added to the system. So if your goal is to define, for example, a new mechanism, you can say, you know, in this condition, acetylene is added all the time, or I add these pHs, for example. But you also see how the structure is changing and the formation, the transition from bidimensional, so 2D structures, to those complicated 3D nanostructures, basically. Showing up also, for example, with curvature. That is one of the important features that we were talking about even yesterday. Yes?
So do you do at each step some type of geometry optimization to get those 3D samples? Okay.
Yes. And so this is an example of this is one trajectory, remember, but this is a type of structures that we can produce with the systems. Of course, there is an entire world that comes after and we're still working on, because, you know, if you have your seed and now there is a random number generator, you remember, so you can have different trajectories. So from this guy, I have, let's say, thousands of trajectories. How do you average them? Okay, so what is this is an interesting question that we're working on. What is the minimum information that you need to describe these nanoparticles? Okay, so if you think about that, from my benzene here, just in the position of A, B, C, as I was mentioning, you can go a different way. You know, every time you run the cycle. So this one can lead you to something that is very weird as a nanoparticle. This one can lead you to something that is a spherical. And this maybe leads you to something that is more like a shape like this. Okay, you don't know. You have information about the structure, the chemical composition, but the structures changes because the pathway that they choose are different. And so how do you do that? The question is at this point, okay, at time, I don't know, 0.5 milliseconds, or if I am 1 millimeters from the burner, for example, I have this distribution. How do I average? What is it? And so what information do you need to describe that? So what we were talking a little bit before and yesterday. Is the mass that you describe? Do you need the shape? Do you need an aspect ratio? Do you need the moment of inertia? What is the minimum? If you want, it's a little bit like you know, forensics. So if you have like a skeleton or something, then you can, more an algorithm for machine learning. But anyway, can you build back the face of the person, for example, from the... So what is the minimum information that you need to go back to my nanoparticles? So this is something that we are very much interested in developing also. Okay, so kinetic Monte Carlo grows structures. The advantage is that first you know how they look like, don't look like spheres, okay? Yes, sorry.
So, if I understand it correctly, you're using a random number generator to attach the groups as you're running your algorithm. But that means that if you repeat the same computational experiment once or twice, you could get completely different answers. So how do you...
So the random number, you will change the random number. Again, you want a stochastic distribution of the system. So what you do is basically you run the simulation with different random numbers all the time. So you want to be as comprehensive as possible in your simulations. And you are running a lot of simulations also. to make sure that that doesn't happen. But the problem is that this is all great, but again, you have to find a way to average those things because, again, if I'm talking with a company or an industry, they don't care that my nanoparticle look like a blob, okay? They want to know how much nanoparticle you form. So for us, the interest was more like, so what do you do with this tool? Okay, one I saw that I told you, I know my shape, I know my chemical composition. You can do some study, this is one example, like a big example. So you can see over time, for example, how do the hydrogen-carbon ratio changes, okay? So if you grow in size, eventually soot has a very low amount of hydrogen, more carbon, and so that can tell you over time, you know, if you keep running, what are the chemical composition, hydrogen-carbon ratio, how does the mass goes? And what is the radius, for example, of the structure. So there are all parameters that evolve over time. Here, the three curves are basically, they were just done with the sensitivity. So if I remove all the 5-member reactions, what happened, how the growth is affected. So you can also weight the importance of different pathways in the type of structures that you do. The other thing that was interesting, maybe coming back to the question I had yesterday, is this. So what we saw, we ran the simulations in same flame. So there were, one was this type of simulation. One was like an aliphatic flame, another one was a benzene, so aromatic versus aliphatic flame. And what we saw that for the same height, the same, we got structures that they look very different, okay? And so what was the reason for that? The interesting part is that if you have an aliphatic flame, you will get something in this condition that were more flaky. If you get an aromatic, something that is more round, like a ball. And the reason for that is that when you have a benzene, if your initial fuel is a benzene, then you will go, you know, eventually you will remove a hydrogen, you will start forming more aromatic from the beginning, in which you have 1-member ring, 2-member rings, and 5-member rings also. And so they will drive the growth initially. And so you will see something that also has a curvature and is way more aromatic. If you have an ethylene, if you think about this, you have a C2H4, he first has to break down. You have to go to acetylene and C3H3, and then eventually you grow back to benzene. So the precursors, the chemistry in the gas phase is different. And that's my input to my SNAPS code. And so what you see here is the effect of the gas phase as a pathway to describe the growth of these nanomaterials. So they can tell you, SNAPS can tell you also how the gas phase environment is affecting the morphology of those nanoparticles that you form. So ideally, we can grow structures, we can go big structures based on this, but the goal, eventually longer time scale for me, is once you have this information, things that you might be interested in computing is, besides the hydrogen-carbon ratio, but what about radical concentration? That's very important. Some people are starting, like the group in Italy is trying to start measuring in Naples those radicals, for example, on the structures. Can we compare with them? Or when you talk about the health, the amount of radicals is very important for the biological process. So you can say, you know, this fuel may be producing this condition more radicals on the structures. The functional groups distribution, this is another thing. So for example, you know that if you really have a double bond, it's easier to get to a soot than if you don't. Morphology, optical properties. So eventually, and again, I'm telling you future interested in. So optical properties, once you have a structure, you can look at, you can compute the spectrum. And so you can see the absorption spectra of those nanoparticles. You know that those emissions have an influence on in the atmosphere, on the environment, incoming radiation. And so the structures influence this interaction. So having eventually really this XYZ of this nanostructure, then you can compute maybe with DFT, time binding DFT, some spectrum. Porosity, surface area, those are also interesting, and density of those particles. So anyway, this is a modeling. So I want to show you a comparison with experiments because eventually you can tell me, as usually, that you can model whatever. So you need some kind of balance. This is an example. This is a collaboration we had with Sandia, and they had a counterflow acetylene oxygen flame. So a counterflow is you have two different burners facing each other, and the flame is stabilized here. So in this case, this is just a cartoon, but you had acetylene argon, oxygen argon, and then the flame front and the formation of soot. So the question for us was more like they could measure materials in the flame. They will sample, and the thing is for us is that can you model this? And so the type of experiments that they had is called the flame sampling aerosol mass spectrometry with ultraviolet, vacuum ultraviolet single photoionization. It's very complicated. But the idea is that you probe, you go in the flame, here, that's the flame, that's the real counterflow flame is how it looks like. You probe the material out, and then you go through a series of processes in which the material is condensed on a lens also, and you basically look at the composition of those particles. And so what they measure is this kind of a mass spectra. So they can measure a different height in the flame, what kind of composition do you have? And it's plotted not like a concentration at this point, but it's more like a mass. So they can say, I found this species that has a mass, I don't know, 200 in this height, okay? And again, they have a mass, they don't have structures. And so the first comparison that we did for this study was something that looked like this. So this was the mass spectra that they measured in the flame, and this is the results that we got initially with the snaps. So if you would run this with another chemkin or mechanism that you know right now, you will not get this distribution. And again, the difference is that I don't need to know this compound. Monte Carlo is building compounds based on the rate. Okay, and so you can find the new structures that you were not thinking about before. We also look at the formation of nanoparticle in terms of structures, and this is just another example which we grew structures in different location of the flame. And what we saw, first you see a different growth, of course, because in some condition you don't grow much, in some condition you grow more. When the temperature is low, so function of the temperature, function of the radicals, function of the number of concentration of pHs that you have. But in other conditions, so you can see the formation of different species, different shapes, and different concentration of oxygen, like the interaction with oxygen, so were added also to the nanostructures. One of the latest one that I want to show you here is the latest we call SNAPS 2 because we are doing more improvement all the time. But right now, the one we have is the last modification, a high computational, the performance we had to increase. And so we can run right now 1 million of molecules within 1 week if you like 48 cores. Was someone asking about the cores right now? So that's some of the advantages. And so right now we have 288, I think that's the reaction. I think we have also more. So we implemented the reactions as a list of, so that's the question also. We need to provide the system with this. You need to translate in something that is based on site, not on the specific species. And of course, there are approximations. Because some rates comes from ab initio calculation, they're very accurate, but some are also extrapolated, and also there is another issue. If I compute, the hydrogen abstraction from benzene, will the value be the same if I have an hydrogen abstraction from a blob? Maybe yes, maybe not. Okay? When you have a blob, then you can have multiple radicals on the species. So does the presence of another radical affect the rate that you have? So it is more complicated than just having a simple compound. Here I want to show you some work that we're doing right now because evidence, as I was showing you at the beginning, presented the oxygen in the system. And so we studied some reaction pathways, so, and also the rates, something that I showed you before. So we started, for example, from a benzene here, and we look what happened to it once you have OH and other species. And what we found, this is basically the barrier to form species, but the idea is that there is a lot of chemistry going on between oxygen and pHs, and all those barriers are possible, so are low enough that can happen in combustion. And so we define some mechanisms that go, for example, from a benzene in this condition all the way through those steps, all the way to the formation of this benzofurane, okay, that we saw in flames. The reason why, besides the fact that, again, some pathways are missing, and so we're trying to cover that kind of questions, this is very carcinogenic. So, and there was no model before that was accounting for the formation of this compound starting from an hydrocarbons and an oxygen flames. So more chemistry, but I just want to make the point that, you know, we're studying this with oxygenated and then building bigger structure with oxygen. I'm not describing this. And so the last thing is the latest work is basically this one that we just published in Carbon, in which we had the counterflow diffusion flame. It was a little bit different, it was an ethylene one. And we compare with improved rates. We improved the description. And so this is, again, the spectra with the same technique that I showed you before, compared with the experiment, with the modeling from our SNAPS code that we have. So we are in the middle of this, and we are not done. Again, this is a tool, but I think it has a lot of potential. What we are doing right now is try to understand what are the pathways also that drive those things. And so this is actually what I want to, sorry, this is what the latest version is of SNAPS 2 actually. We have 417 reactions, so my students will be mad if I don't say this correctly. He's been working on this with his PhD. So, so yes, a 417 reaction, and right now we have not only the HACA that we talked about, so acetylene is playing a role, but we try to include everything that is also in the literature, so the C3, furane, we can close the zigzag, the bay closure that I was mentioning before, so we have all those options in here. Okay, so let me see this one. The last reason to do that is that we saw this species again in which you have this bigger pH. In some condition, we found those pHs with a lot of oxygen on it. And this goes with one of the, in the same flame, this goes with one of the experiments I showed you at the beginning. They were saying in the spectrum, the red peaks are from oxygen. So now with this new chemistry, we are able to somehow describe some of the peaks that they see experimentally. Okay, so that's where we stand with the Monte Carlo. That's where we stand with our understanding of nanoparticles. So we have those tools we are using to get a feeling of what are the pathways, whether you're running with just a physical interaction, like a dimer-dimer, and what kind of structures the dimer needs to have to be a nuclei, basically for Soot. And on the other side, we are also going through the second pathway that is chemical, because SNAPS here is only chemistry. Okay, there is no physical interaction at this point. And so we are doing both of them. We are trying to see how the fuel influences the pathway, and we're also trying to describe those nanoparticles in a more complex way, if you want, and try to translate that in a model. Now, on the line of what I showed you before is that the next step is for us to add the physical interaction. So once we have those bigger structures, we want to see if they get together. You remember we talked about coalescence. And so coarse graining of those structures. And again, this is a simplification, something I mentioned yesterday, but I found what I was looking for yesterday, so I want to show you. So the coarse graining means, now I have this blob. Can I describe in an easier way so that computation is affordable? So this is methanol, right? This is a simple molecule. I just want to give you an example in which you have a CH3 and OH. And instead of having CH3, I'm going to replace the CH3 with one site and OH with another site. Okay, so this is coarse graining, if you want. The tricky part is that you need to define this interaction, because now it's no longer the fully atomistic, but you are simplifying the system, reducing the complexity. And so we did that. And so the structures I was mentioning yesterday, you have those 3 points. You know, this bigger structure can become 3 points. And so the next step to what the SNAPS was doing is try to see if those structures coalescence. And so the bigger structures. And what we saw with the molecular dynamics simulation is that, first of all, if you start putting together nanoparticles in a big box, you have a lot of those. This is just an example, but it shows you that on the left, if your nanoparticle are all kind of round shaped, like a ball, you know, they really form clusters. If they are more flaky or flat, they have more problems getting together, and they form subclusters. So this speaks to the entropic contribution, not only at the attraction, the enthalpic ones. And if you have a mixture like a 50 and 50, for example, of them, you have a different behavior again. So morphology plays a role. When you move in the mechanism for Soot, the models for Soot, as I was mentioning the first day, it's not a sphere. It's something that is complicated, something that has a morphology, and the morphology plays a role on the rate. So it's not that sphere 1 plus sphere 2 becomes a bigger sphere, but we need to somehow rethink or implement a different, maybe a different rate that takes into account those properties, okay? And again, you go back to the question, what are the properties that you need to preserve or you need to describe the behavior of nanoparticles? This is a movie I was looking for yesterday. So this is the 10,000 particles, 10,000, yeah, and so each particle is a dot for you, because that was what you see in this movie is basically the formation of those more spherical. So if you look here, I think those two will get together and will form a spherical blob. Something will happen here too, if I remember. So we are trying to move up in scale and see how, if I consider, for example, well, all around the nanoparticle. So here, this guy is getting together. You remember we talked about coalescence, that those clusters will get together and form spheres. So here we start seeing something on those lines. Of course, this is simulations, this is all way around particles, but the next step for us is taking information for this atomistic scenario in which you have a morphology, try to carry over the morphology to different scales, and try to grow in size on the line that I showed you before. Okay, so I want to conclude this part of with some needs again. I think open questions also. So there is a huge need again for uncertainty in the chemical composition of pHs. So anything from the modeling perspective in terms of chemical pathway is very important at this point. Rates, always, but also refinement of kinetic models. And what I mean by refinement is that what are the pathways missing? What's in the mechanism you're not taking into account that can help you to better match those experiments? And so pHs, chemistry, experiments and model is a huge need. And of course, this goes also with the experimental technique in the area of nanoparticles that could be useful. As an open question, I just listed the sum that, you know, just to kind of get you some ideas. And so still, we don't know much about what is the nucleation and what is the growth. So here I show you some hypotheses. There is a physical pathway. There is also a chemical pathway. Depending on the flame condition, one will be more important than the others, okay? So chemistry will drive a high temperature if you have a lot of radicals. If you have a lower temperature, if you have a lot of pHs, for example, they will cluster. As I showed you yesterday, lower temperature and pHs will cluster. How do the condition, that's what I was mentioning in the flame, can affect this growth? How the particle physically and chemically evolve? So one of the simulations was taking this nanoparticle and see if they form these coalescent structures, for example. We are also very much interested in oxidation of soot. So that is a further scale for us. And then overall, the importance of particle structures, whether it's chemistry or morphology, it's really interesting, especially for the health effect. Okay, so again, one ideal scenario is what you have some fuel, and you can say this fuel formed this type of nanoparticle with this morphology, and they cause troubles to the cells in the body. Okay, so basically that would be another. Okay, so I think I'm going to stop here. The idea was to give you an overview. The idea is that there is something that we know about the formation of pHs all the way to nanoparticles, coalescence, coagulation, and soot. There are some models that are available. There is a lot going on, but there is also a need to address some specific questions. The tools have been showing you, even if it was like really a glimpse because of the time and because some of those require some deeper understanding, reading, but there are different tools that you can bring to the tables, and they go beyond just studying a reaction, because you can answer way more different questions. The role of those tools is to help the modeling somehow. They provide some mechanism, some molecular answers to some of the questions that you might have. So why this fuel is forming this pH and not another pH, for example, or why the structures of this nanoparticle is round instead of being flaky, just to give you another. Once you have this, you can also talk about pathways of growth. So you can say, if I have a benzene flame, the molecules that you keep adding is this a C? Okay, so if you're developing a mechanism, maybe you want to think of C as a dominant species. Think about the Haka with acetylene. So this is another question that you can answer. And overall, I think those are the questions that everybody's still asking in the field, and with the overall goal to define the models for soot. My interest is more in the pHs and the transition to nanoparticles, so not too much in the bigger size of the soot, because I think those are the building blocks for whatever happens later. So at this point, I think I'm going to stop the the combustion part, and I want to use the remaining for talking about two other projects that we have. And unless you guys have some questions that would like me to, yes?
Do your models provide any information on, like, the opposite, basically how to prevent soot formation? Right, so what do you learn in that regards?
Yeah. So, yeah, that's a great question. So I don't know if everybody heard the questions, but his question is that can we understand something also about how to prevent that? So, great question. So in the moment you're trying to understand from atomistic simulation, from a basic level, what's happening. So the idea is that eventually, for example, you will see here that you keep adding C. I'll just give you an example. So what you want to do is maybe see if C can be reduced in those conditions. But you need a model that is accurate. So the first day was about prediction. If your model is robust enough that can be predictive, and by predictive I mean that not only reproduce known condition, but also unknown scenarios in which your experiment had never gone to, for example, then you can talk about also control, because the idea of all this learning is to control eventually. So to answer your question, the answer to your question is yes. In the moment I know and I'm confident that this is the real pathway, the C, for example, keeps adding and is what's causing the growth. In principle, you could find a way to prevent C or limit C, ideally.
So in terms of the graphic that you opened the lecture with on the first day, the time scale
Yes.
and formation of pH, and then nanoparticles, so the most impactful time slot to prevent soot formation occurs at this point. That's your understanding as a community.
So partial, yes, I agree with you. My interest in the nanoparticle is because, again, first, those are the nuclei that eventually become soot. So if your model is telling me this is a sphere and I keep growing, this is not, it's part of the story, but it's not the complete story. So definitely I want to understand those seeds, those nucleation, the transition from the gas phase to the particles. If you understand that, maybe you can stop that somehow, in principle. And the other thing is that nanoparticles are really concerned for the health. there is no way you can stop them, basically. And so that's what they get in the environment. That's what we breathe every day, if you want. That was one of the driving interests. And the other thing is that, as I'm going to show you right now, nanomaterials, they are formed in combustion. So if I find a way to define this gas phase and inception into nanoparticles, then I can apply also to different materials in a flame. So again, it's about applications that you want to think. Just not think about one reaction, but think about the power of this tool. Can go beyond. Yeah. Any other question here? So I'm going 10 more minutes. Is that okay? Yeah. Okay. So I want to show you an example here. So this is a cartoon, but I want to show you MD in terms of chemistry, and I see that as a various application, as I've been mentioning since Monday. But some of those is biology, mechanics, physics, and material science. So one example I want to take today, one little bit of time for this material, and the other one I'll talk about biology. So we had a project with an experimental group who was basically growing powders of alumina in liquid flame spray conditions. Okay, and they were specifically interested in understanding how the conditions of the flame were driving the type of nanoparticle that you form. So when you have alumina, you can have different phases, and this is maybe an alpha phase that you can have, but you can have theta, delta. It depends on the disposition of those. So alumina is Al2O3, first of all, I should say that. And so this is the atoms that you can have. They can have a different organization, so aluminum and oxygen. And so there wasn't a flame, fine. But you can have also something that is a little bit different, that is more like a theta. So you can see the disposition of Al2O3 is different. So the question was for us, if I have nanoparticles of alumina and nanoparticles of alpha and theta, what is the, when they put in a flame and they grow, for example, like they get together, like something like the coalescent that I showed you before, you say, what kind of phase do I get and why? Okay, so that we can control again. So if I tell you that in this condition I form theta, for example, then change the condition if you want alpha, just to give you an example, or control the temperature. And so we did some molecular dynamic simulations for that. So this was we're trying to look at what they call sintering. So if I have two nanoparticles, one was alpha with the configuration I showed you before, and the other one was theta. If I get them together in a flame and they coalescence and form this bigger blob, what kind of phases will you have? And so with molecular dynamics simulations, the first thing that we did, this is, before I show you the simulation, this is the experimental data. So experimental, you can use an XRD to look at the structures of those nanoparticles in a flame. And what they saw here was that depending on the size of the structures that you have, you can have spikes here, or you can have a broader distribution of the system. So you can have more a crystalline phase in which you have a specific spike, or you can have something broader in which you start seeing this kind of liquid-like on the side. Okay, so we look at those same sides with molecular dynamic, and so we went from something that was a solid, for example, was a 4 nanometers, you had a very solid structures, and then eventually, as a function of the temperature, you can also form this kind of a melting stage as amorphous structures. So what we did was this type of simulation. Maybe this is the best way. So you cannot see easily here, but what you do is taking molecular dynamics, you take the structures, and first of all, you need to identify what diameters you have. And that's the reason why you compare with the XRD in the first stage. And so knowing that you are in those conditions, you find your structures that better represent the experimental value. And then we ran simulations of MD. This was a bigger simulations. And we took 2 nanoparticles that were one alpha and one were theta. And you basically let them sintering, so they get together, spend time together with a temperature. And the idea is that what happened at the end? What kind of configuration can you get? And how the temperature is affecting those final configurations. So in the final blob that you will see in a second, the question is the arrangement of aluminum and oxygen. Is this going to be theta or alpha? Okay, and so those are questions that MD again can answer with the system. And what we found is basically that once you put them together, the result is, you have this alpha configuration. And this was due to the diffusivity of oxygen atoms between the two systems that create this kind of thing. And what I'm showing here, and maybe, I don't know if the graph is completely clear, but basically this is a comparison between the XRD that we computed from molecular dynamic simulation with the experiments, and we matched the peak very nicely. So the molecular dynamic simulation was able to agree with the kind of phase that we're seeing experimentally. And so the way you use that, again, is that you can tell you this condition, this temperature is affecting the phase of your nanostructures. This is the type of nanostructure that you can form in these conditions. And so the reason is also the oxygen diffusivity, but the point is that you can predict somehow what's happening to the phase of a particle that you can have. They were very much interested in nanopowders, so of this substance. But if you, for example, want to produce alpha, you know that if you mix with those type of precursors, this is the type of nanoparticle that you get at the end. So a little bit different from what I'm talking about, but the idea is the same. I'm using MD to predict the type of structures that you have in a flame, given some initial precursors, that is theta and alpha at this point. So this is just an estimate. So this is just showing you exactly what I told you before. So the sintering, you have alpha nanoparticles with the theta. This is what nanoparticles, the theta phase transition to an alpha, basically. And so your final blob is going to be something that looks like this, and compared with XRD. Okay, so I'm going to stop here. That was it. And then I will use the last part